Very good morning, all of you. So today we will give a demo on a rapid prototyping machine. In our college, we have two machines. So now we are going to demonstrate only one machine. So give the demo on one machine. Over to Chandan.
Fine. Now, at our college, we have two RPT machines. Okay, one is flash code. Both the machines are from a flash code company. One is with respect to FDM, and another one is with respect to stereo lithography. So, since the components you make from stereo lithography takes a lot of time, so I'll try to give a demo on PLA because here components can be made very small. So, in half an hour, even though you try to put a model, so it gets printed in half an hour. Now, I'll just share my screen regarding what type of machines we have and what are the specifications of the machine. What are the specifications of the machine I'll show, and what are the materials that can be used in that machine corresponding to that machine, which is basically on FDM process. Okay. Machine parameters, and we also do take small amount of consultancy work here, but we will try to show the components of that. And while printing those, what are the problems we face? Even that will be discussed. And at the later stage, if you have any queries with respect to this process, I'll try to answer. So I'll just share my screen regarding the mission parameters. So we have, this is the one which is flash code. Okay, we have, this is the machine what we have at the college. Okay. So this is called the flash code Dreamer. We have, this is the machine what we have at the college. So flash code Dreamer. So it is basically it has got two extruders. Your machine comes with different extruders in different temperatures. What we have dual nozzle, basically dual nozzle, so that you can combine materials, different materials and different colors. You can use an ABS, you can use a PLA. Okay. Now, and it is directly extrusion, and the size of the component that can be printed here is somewhere around 230 cross 150 cross 140, which is almost 14 centimeters, 15 centimeters, and 23 centimeters. Okay, in size. That's the volume. And even it has got a heated bed facility because some machines don't have this. We have a heated bed feature here. Okay. So now, okay, this is some of the specifications of the device what we have. Okay. So the maximum temperature of the bed that we are doing only with respect to PLA and ABS because the finish that we get is very good in ABS compared to PLA. And PET-G and TPU95A we have not procured. So, and also something with respect to which are the software that you have to use, that also I'll be discussing. And coming to the filament that we use here in our lab. Okay. So we have filament. Okay, now, so these filaments come in like 0.5 kg and 1 kg. Okay, it's a reel, and the filament material, as I said, the PLA as well as ABS comes in different colors. So, irrespective of the color, the cost is always same. Okay. So what we have, cost is always same. So here you can see it's somewhere around 1,200 per reel. That is for 600 grams. Okay, it costs around 1,200 per reel, and it's 600 grams basically. So here you can see basic different combinations, okay, of PLA. Similarly, ABS also you get. Okay, so this is a resin, which is photosynthetic resin that is for a different material, for a different machine. Now, which are the software that we use in order to while making a 3D model as well as how we post process that, okay, before we entering it to the machine. So you can use any 3D modeling software like CATIA or any 3D modeling software you can use. Once it has been modeled, you convert it into STL file. So whatever STL file you get, okay, that will be imported into this software which is given by the machine provider. So this is the software which is called Flash Print, which can easily be downloaded. So already have this machine. Okay. So here this is what you get. You get to do something like this. Now here inside this, once you have saved an STL file, so you will be importing that STL file into this. So for as an example, you have inbuilt components here. I take one of the components. So like once you import an STL file, this is how you get it. This is your component. Okay, you can rotate and you can make sure you can even move this and also view what are the different views you can get top view, okay, bottom view, similar to any 3D modeling. So all the views can be seen here. All the views can be seen here. Now you can even move because sometimes, right? So what you have to do is you have to fix your model to some exactly on the bottom of the bed. So you can move your component, okay, onto the platform center. Like you can give some positions. So it is moved 20 mm to along its axis. So just reset it. Similarly, you can move your component so that the component is placed exactly at the center. Okay, and you get a very good print. I'll just reset this. Now, one advantage of this CLA is you can print intricate shape, okay, not just regular dimensions, very intricate designs. And the designs are very intricate. Let us say you have a hollow cube. So inside a hollow cube, you can even place a sphere, hollow sphere, because your cube is completely enclosed, but you have a cube inside. So these types of components can be done in this, and you can rotate that. Okay. So this option is rotate because when you read, when sometimes in a component, what happens is when we try to print it in a machine, it creates something called support structures. So support structures, in order to, because it is not required by printing, okay, it should not be there in fact, because sometimes when you have an extension of component, you have an extension of the component, similar to a cantilever beam or something like that. So when we try to print that, so we need a support structure. So sometimes we can eliminate those support structures by using by just rotating the component and using common sense and trying to place it in such a way that you can try to avoid getting a support structure. Now you can even scale your component. Okay, so let us say I'll scale it. Okay, you can scale your component, and finally I'll just reset it. So this is how you can do this one. And extruder, which extruder you're trying to use, whether you're using a left extruder or right extruder. So use right extruder as given. And if you want to draw something, with respect to mouse, you can use this. For this example, we're not doing anything. Now, once the component is loaded here, let's see what are the other processes that has to be incorporated before we put the same model into the machine. Now, coming to support, okay, support options you have. Now, you can have support, okay, while printing. The support structure can be tree-like or it can be linear. So if it's a tree-like, the base diameter are given as 6 mm. Okay, post diameter that is like similar to branches is 6 mm. Okay, and all the branches are 3 mm, and the height of the stem is 6 mm. If that is set of default, okay, and if you give auto support, as you can see here, okay, these are the support structures what I was telling about, and these are the branches. So while printing this layer, so when the machine tries to print, okay, when the machine tries to print this layer, it needs some support because it cannot print in air. So this acts like a support, and this component can be printed. So if you don't want tree-like, okay, you can even delete the support you want shear support, and you can change the support option. If you make it linear, everything is like a column, pillars. So here the pillar size is 1.5 and 1 So even you can change the pillar size also. So this is how you get in order to build the support. And here you can even see if you remove the component, how the support structures look like. So the support structures look like. And if you want to delete two support structures, you can even delete. Let's say it's not necessary, I don't want that, you can delete that. So just show you even with respect to 3. So auto support, delete auto support, and if you try to mask the component, okay, this is what you get. So 3 like, so you can delete some of the supports if you think, and you can even add supports, okay, wherever you think it is necessary. Like let's say at this point I want support here. Okay. Okay. So this is how you build a support. Once the support is built, something like this. Okay. So what you can do is you can just go back, and the entire file will be saved with an extension.txt. Okay. So after that, you can give print. So which is the material that you want to print? Whether you want to use ABS material or whether you want PLA material, that is what we have. So let's say I have PLA, okay, right extruded as well as left extruded, both are PLA. Otherwise, if you want, you can even change that individually. So PLA supports required or not, and this is RAP. I'll just explain what is RAP. RAP is like nothing but a foundation for which a component will be built. And what type of resolution you require? So you require the printing to be very fast. Okay, so if printing is very fast, you won't get a very good resolution, and similar to that. So it's better to keep by default what you have standard, that works fine until unless the people who are giving components to print ask for a specific configuration. And whether you want a boundary like a brim or not, let's say. Other option is what is the height of the layer? The first layer height where it's 0.18 mm. Okay. So by default it is 0.18 mm. It can change up to 0.15. Okay. And similarly, shell parameters. So the entire 3D volume, how it is built. Okay, how the entire 3D volume is built. I'll just show you that here in this. And fill density. We want the entire volume to be completely filled, or you want hollow inside. So depending upon that, you can change here. Let us say I want it 70% filled. That is your filling. And filling pattern. When I say filling pattern, whether you want it in the form of line, okay, hexagon, triangle, 3D fill. So a few components are shown. So we have here a cube. Basically, I'll just show you a skeleton of a cube. So this cube, what we have here, this is basically hexagon. So it's basically a cube which was printed, and at some point of time, because of power loss, okay, we had to stop the machine by doing some trial and error method. So here, this is how it will be constructed. So this is somewhere around 20% fill. So for 20% fill, inside you'll be having a honeycomb structure. Outside you'll be having a complete solid layer. So this is what we need by feed. And speed, by default, we have not changed any speed as of now. Everything is working fine at 60 mm per second, as well as travel speed of the printer head, 80 mm per second is also working fine. And the temperatures, depending upon the material that you use, whether you use the PLA or ABS. So PLA says that it's enough for if the normal temperature is somewhere around 200 degrees and the platform is 50, but as per our experience, platform when it is at 50, we try to peel out. Before the component is even printed, your platform tries to peel out. So it's better to keep the platform as 100. So that is what we do. and right extruder at 230 for both for ADS as well as for PLA. This is fine. 230 is the melting temperature of or the temperature of the nozzle or melting temperature of the fluid, and the platform temperature is 150. So when everything is done, so you can give OK. So it will ask you where I have to save this. So let's save it. .gx. The file extension is .gx. So once it is saved, I've given 20% free density. Okay. So, so it takes almost around 1.5 minutes to print this, and the material estimated is somewhere around 5.4 meters of material. And if I'm using a PLA, okay, the component weight will be somewhere around 16 grams. What we charge here is, earlier it was with respect to time. For 1 minute, we used to charge somewhere around 6 rupees, but due to competition, we have reduced that. Now it is everything with respect to grams. What is the weight of the component? So the weight of the component is per gram, we are selling somewhere around 6 to 8 rupees, depending upon again material. PLA, it is a little bit less, and if it is ADS, it's likely costly by 1 rupee. That's it. So 16 grams is 16 grams into 8 rupees. So that will be the charge of this component. So, but it takes 1 hour 45 minutes to print this. And layer by layer, as I said, layer by layer, it tries to print. You can use this slider to see this is the foundation. Initially, it will try to set, because even though if you don't allow this foundation to be laid, and if you want to build a component as it is, because there is a certain amount of vibration in the machine, and when the nozzle tries to move over this layer by layer, sometimes there are chances that it will topple, the component will topple. Okay, a piece will break. So it is better to have this wrap. This is called a wrap. So as you can see here, given hexagonal combination, so the volume is getting filled with the hexagonal honeycomb, okay, structure, and even similarly the trees are getting built. So this is how layer by layer the material gets built. So now, since we don't have 1 hour 45 minutes, now we'll try to reduce the scale down the component, and we'll try to print it. Or even I can give a field density of somewhere around 30. But if I give field density of 30, again the trees won't be strong enough, so it will the trees may break. So what I'll try to do is I'll try to scale the component itself. Or I'll take a simple example. This itself. And I'll try to scale it. So it's almost 3 centimeter cube it is. So I don't want 3 centimeter cube, I'll just give you 1 centimeter. 1 centimeter cube. So this will be my 1 centimeter cube. And you check with the extent of the platform. Based on the platform. So suppose by default this is the water So suppose option is 3, I'll reduce the base diameter. And the post diameter even then. So I'll take out this platform. Then give I take out text platform only. So this is how we get. As you can see, the trees are very thick. Okay, you can reduce the thickness of the trees. Yes. So base diameter not reduce. Not keep it as 1. This can done by plus 3. Even now, while printing, there is a difficulty of manufacturing this. These things, what you get, they tend to make while printing. So I doubt whether this can be printed. So not take this. We take a simpler one just to demonstrate. We can into this. Again, a scale down. Along with that was and I don't think this got any support. Make sure that it stays on the platform. And this doesn't require any support. Try to print it with PLA fiber. And I don't want any building walls for this since it's a trial run. So you can here try to make sure that it's somewhere around 50% minimum and it's single pattern. So try to take the temperatures. It is 230 and the platform temperature be 100. So let's start. So this is how you get. Okay, so the estimated time is just 4 minutes, and the material is 0.19 meter, and it is taking PLA and material is 0.57 grams. It will be built in using 27 days. Fine. And also I'll show you some of the defects while manufacturing. Some other components that right through. Now once this is done, it is already saved. Okay, it's already saved using .gx. We have this .gx. This file using the SD card. I'll try to put it onto the SD card and into the machine. Since it takes only 4 minutes to print, I'll demonstrate that. We have one more thing which is called 3D scanner. Okay, so this 3D scanner, again it is from Matter and Form. Okay, so we have a 3D scanner from Matter and Form. Okay. So this is a 3D printer what we have. The same 3D printer we have. So you have a 3D component, a small tabletop component which you want to. This is the one we have. So the small component has to be placed onto the base here, somewhere on the base. Once not on the base, and you connect it to your machine and you can start scanning. Once the component is got, you can take 3D shapes from that. Okay, that 3D component volume, and you can take it and print it in a 3D machine. And you have a software for that. This is the software that we have. Let us say even a small a rubber frog, just to make sure that whether all the curves, because when you try to scan, okay, with indicate shapes, corners and all, everything should be properly available. So if you have a small rubber component, so I've already scanned that. So when you try to scan it, okay, so these are the points that it will try to acquire. So you have a point that it will try to acquire. Once the points are acquired, you just have to mesh those points, connect those points with one surface. So I've already done that. Okay, it will take almost 10 minutes in order to scan, depending upon the volume, okay, and other features. Now, once it is what is the volume, what is the surface area, how many cases it has created, everything it will give. So finally, this is the component that you have, and you can export this model. Okay, you can save this. That's already big enough. Okay, I'll show you how to export this. Okay, and save it in STL file and put it onto the machine for printing. Now I try to demonstrate the machine. So we already have a GX file. This is okay. So now what we have, this is basically a COVID material headband. What we have, you can see. So using an OHP sheet, you can convert it to COVID material. Sorry, COVID-19 headband. Similarly, some tensile specimens have been done for research purpose to be okay, to test because this is completely solid, 100% solid. In fact, 100% solid is not required because ABS material, the entire ultimate strength, everything will be known. You can change the cross section and you can change the cross section. You can change the cross. You can change the field density. Change the field density of this. Okay, and you can do some research on this. Similarly, some box for some companies, or whatever components we have are components where we face a problem and it is not completely print. It is basically half print because the complete component cannot be shown because it is proprietary of the company. These are the components which are printed into half. At the halfway, it was stopped. So this material also was stopped half away because there's a peeling effect. So once the component was printed, so the further component which was being printed above, because one layer had peeled out. So because of that peeling, what happened was it was not sticking. So that was one problem which was faced. I don't know, maybe with respect to temperature effect, or maybe the component became very large. Okay. Now again we have manifold, intake manifold, which was done. This material is ABS. So the finish also what we have got is very good compared to PLA. All other components are PL. Okay. So similarly, some hose. Okay, some hose. These are all prototypes. Okay. So the machine what you have. So as you can see, so you have a dual extruder. Okay, you have a PLA rim. So 1 kg. You have a heating bed. Okay, with a touchscreen interface. So initially you have a preheat. Now let me put it to preheat. So once I put it to preheat, so it is asking me what is the temperature. Left extruder temperature 230, right extruder temperature is 230, and platform is 100. So I don't want the left extruder to work. I'll switch it off. Okay, and I'll just try to give it a preheat. So in under 2 minutes, it gets heated. The platform is already heating at 30, right extruder at 35. I'll just use a Pause mode. At the streamer. Stream on video. So now I'll show you how this speed meter works. Okay. So that means this is software enough. So new. So I'll give it as Preheating. So in this, basically we have a 3D scanner. Okay. We have a volume one. On. Okay. Now, what we have here is a 3D scanner. Okay. This is the 3D scanner. What you have. If you are able to see the book scanner material. No? Did add. So. Fine. So this 3D scanner, as you can see, this is the component which has got intricate shapes. Okay. Similarly, any other component can be kept. Now, this is a small platform, so not very big components can be done. Not a very big components cannot be done. Okay, or scanned in this what we have machine. So this is a small component just to check. So you have a rotating platform, basically it completely rotates completely 360 degree, and you have two laser lights here with one camera at the center. So place your objects whichever you want to scan, and using the software, let's start a new scan. So it says that estimated scan time is somewhere around 1 hour 38 minutes and 14 seconds. Okay, we'll try. So you can see that the lights from the laser, okay, you have two lights, one is showing almost yellow and one is green, fine. With regular scan, let's not, it says that it takes around 98 minutes. We'll try to stop it somewhere around 10 minutes. We'll see what is the, as you can By the time it gets scanned, okay. So I'll just show you one more. This is a PLA. Okay, this is we have a PLA rim. Okay, as you can see, it is of diameter 1.5. Okay, it is PLA and the color will be green. Okay, this is the rim that you have. The diameter is 1.75 mm. Okay, now as you can see, the right extruder is almost at 230 and the 100. So you want to print the component. Okay, so now using this is a 20 mm box. We have other also. We have a 20 mm box. Let's try to print it. So estimated time is somewhere around 4 minutes. In 4 minutes, it gets printed. It's a very small component. It's almost 60%. You can see just remove it. So this is how you get it. It's basically a rectangular part, okay, which is one by 1 centimeter, and the I think height is 5 mm. Okay, so this is how it is. It was just printed in somewhere around 4 minutes. Similarly, other parts can be printed. Now let me switch more to the scanning that we had given. So just show the scanning. Stop sharing. So now this is a point that we have got. It says that it's still scanning. Okay, I'll stop at this point. We'll see using only these data points is it possible to create a surface. Uh, Screen share like this. So using only these data points, I've stopped. Using only these data points, I'll try to create a surface. Once it is done, if you want to clean for any noise cancellation, you can see it will crop all these red points if I try to do that. So let me not cancel all those. And after cleaning 0 points has been selected, fine. Meshing with mesh information. The depth of mesh. Okay. with whatever is there if I try to mesh it by using default settings. So this is how the surface was generated over that using those points. So now we can export this, whatever the surface which is generated, to an STL file, and we can print it using 3D printer. Okay, that is it. So if you have any questions, kindly paste it in the comment box. I'll try to answer. Thank you. So including texture, so you get something like this. So this was only scanned for say 14 minutes. So but the time allotted was almost greater than 1 hour. If you try to use all those time, so what you get is contours with entire contour. So here you can see it is not properly finished. Okay, the contour. Okay, at the back of the neck, at the legs. Okay, so if you want all these properly, it has to be scanned properly. But for time being, this is good. So you can export this to an STL file, and we can print it using the 3D printer. Now, if anybody has a
Very good afternoon to all of you. Myself, Raghuyan, working as Assistant Professor in the Department of Mechanical Engineering. On behalf of Vidyavardhaka College of Engineering and Department of Mechanical Engineering, I would like to thank our resource person, Professor Chandan, for enlightening the deeper insight about the rapid prototyping. And also I express my sincere thanks to all the participants for attending the workshop and making this event grand success. Once again, I would like to thank each one of you. Thank you and have a good day.